Hello dear students, welcome back to chemistry classes. Today we are discussing defects continuation part, that is the non-stoichiometric defect. The name itself indicates non-stoichiometric defect, means here the stoichiometry of the crystal lattice is different. For example, NaCl like this. Here stoichiometry is correct, means one sodium, one chlorine, one sodium, one chlorine, like this. But in case of non-stoichiometric defect, some stoichiometry is not observed. Excess of cations and less of anions, or less excess of anions, less of cations, like this they are observed in the non-stoichiometric defect. Okay, in the non-stoichiometric defect, there are two types on the basis of the cations. There is metal excess defect and metal deficiency defect. Non-stoichiometric defects are categorized into two types, that is metal excess defect, metal excess defect, metal excess defect. Another one is metal deficiency defect. Metal deficiency defect. Metal deficiency defect. Metal excess defect and metal deficiency defect. Okay, on the basis, these two defects are observed on the basis of the cation present in the metal. The metal is made up of metal ions, means they are having so many cations. The excess of cations makes the defects. This type of defects are called metal excess defects. The limitation of or absence of cations makes the metal deficiency defect. Let us go one by one. It is a metal excess defect. In case of metal excess defect, what happens here? Take an example of NaCl. I am taking the NaCl here. Here NaCl like this. Cl, Na atoms are arranged in a perfect manner, or what non-stoichiometric ratio. Cl minus. When this crystal, when the stream of the vapors are passed into the crystal, the stream of the sodium vapors are passed into the crystals. Some of the sodiums are accumulated, some of the sodium ions are accumulated on the NaCl crystal, and the chlorine ion is diffused with the sodium. When the chlorine ion is diffused into the crystal with the sodium, it is eliminated as a NaCl, but the electrons are occupied to this anionic site. Electron which is occupied into the anionic site. This site is called what? F center. This site is called F center. What do you mean by F center? F center is nothing but the anionic site. It is occupied by an unpaired electron, means single electron. Anionic site, it is occupied by single electron. That site is called F center. What do you mean by this F center? What do you mean by F? In the Latin word, what? It is called Farbengender. Farbengender. Farbengender means color. Farbengender means color. Carbon gender means color. This presence of this unpaired electrons makes this compound to color. When it get energy, it going to the excited state and it back to its original state. During this excitation and relaxation, this compound shows some color. That color is caused by this electron. That's why metal excess defects show some color. That's why this sign is the F center. One more question will appear in annual examination. What do you mean by what is the F center or define F center? Okay. Okay. Some in the NaCl, it shows yellow color. It shows yellow color. Because of presence of unpaired electron, it shows some magnetic property that is called paramagnetic properties. Okay, it shows paramagnetic property. It shows color compounds, and it shows increased conductivity because of this electron. Okay. There is a NaCl show yellow color and lithium chloride show pink color. Lithium chloride show pink color and lithium chloride show pink color. Okay. KCl show violet color. KCl show one violet color. Like this colors are appear in metal excess defect. Here what happens? Some metals, see why it is called metal excess? Metals are more in number. Metals are in maximum number. Non-metals are less number. That's why this is called metal excess defect. Got it? In metal excess defect, it is one way of metal excess defect. Another way is there, that is the presence of some extra cations in interstitial side of the metal. Okay. Take an example of zinc oxide. First one we learned, that is a cation vacancy. Sorry, anionic vacancy and ionic vacancy. Anionic vacancy. In second one, presence of cation in interstitial site. In interstitial site. Okay, take an example of zinc oxide. Zinc oxide, what happens upon heating? Upon heating, zinc plus 2 and half O2 series. In the crystal, zinc plus 2, oxygen O2, zinc plus 2, oxygen O2. Like this is released. Oxygen is released. Like this arrangement is there before heating. Like this arrangement is there in the anionic vacancy. Upon heating, some of the oxygens are eliminated. Some of the oxygens are means anions are eliminated. But excess of zinc ions are present or occupy the interstitial site. Excess of cations are occupying the interstitial site. This makes the defects. Such type of defects are also called metal excess defects. See here, maximum cations are smaller in size than the anions. That cations occupies the what interstitial site and makes the cation is more. That's why metal excess. That's why this type of defects are called metal excess defects. Okay, got it? Next, metal deficiency defect. In this metal deficiency defect, second one non-stoichiometric. Second non-stoichiometric defect, we can get it for non-stoichiometric defect is metal deficiency defect. What do you mean by this metal deficiency defect? Here, some of the metals are lost. For example, having the two valency, oxygen also having two valency, like this arrangements are appear in the crystal. What happened here? That the oxygen having two valency and pairs having the plus two valencies, both are matched here. When defects is before defects, it is arranged like this. After defect, some of the pairs plus two ions are eliminated. See here, charges are equal to 2, 4, 6, 8, 10, 12 positive charge and 12 positive charge, 12 negative charge, isn't it? 12 positive charge, 12 negative charge. Before defect, after defect, we are using some like this. And removing them. We are adding in order to maintain the electrical neutrality. This side is empty. This side is what? Empty. Now we have to calculate the charges. 2, 3, 5 plus 3, 8 plus 2, 10, 11, 12 positive charges, 2, 4, 6, 8, 10, 12 negative charges. Even though electrical neutrality is maintained, some of the sides are missing. That's why this type of defects is known as what? Metal deficiency defect. In this case, electrical neutrality is maintained. Even though electrical neutrality is maintained, some of the positive ions are missing. Such type of defect is called metal deficiency defect. Got it? Next concept, that is electrical properties. Next concept, it is electrical property. Last defect is there, that is impurity defect. Impurity defect. Now third defect, impurity defect. In this defect, we have the crystal lattice having some impurity in their lattice sites or interstitial site. Such type of defects are called impurity defects. Got it? Next concept, that is electrical properties. solids again classified into three types on the basis of their conductivity. So, what are those? Conductors, insulators, and conductors, insulators, and semiconductors. Conductors means they conduct the electricity either in the molten state or in the solid state. We are studying the solid state here, that's why conductors. We have to study the solid state. Its conductivity is 10 to the power 4 to 10 to the power 7 to 10 to the power 4. Its conductivity lies between the 10 to the power 7 to 10 to the power 4 per ohm per meter. Next, insulator conductivity is 10 to the power minus 20, means it do not conduct the electricity, it do not allow to pass the electricity through it. 10 to the power minus 10 per ohm per meter means it do not conduct the electricity, or it will not, this is not allowed to pass the electric charge through it. Semiconductors means 10 to the power 4 10 to the power minus 6 to 10 to the power 4 per ohm per meter. 10 to the power what? 10 to the power minus 6 to 10 to the power 4 per ohm per meter. On the basis of their conductivity, have to classify the conductors, insulators, and semiconductors. Then, semiconductors. Conductor means what? Which with the substance which conducts the electricity through it, it is called conductors. Insulator means the substance which do not allow the electricity pass through it, it is called insulator. But semiconductors means the conductivity lies between insulators and conductors. It is called semiconductors. Called, for example, silicon, germanium, etc. Okay. Semiconductors are of two types. One is intrinsic semiconductors. Intrinsic semiconductors. Another one is semiconductors, intrinsic semiconductors, and extrinsic semiconductors. Extrinsic semiconductors. One is intrinsic semiconductors, another one is extrinsic semiconductors. What do you mean by this intrinsic semiconductors? These are purely semiconductors, not having semiconductors having impurities. Silicon and germanium, these are the intrinsic semiconductors. In this type of conductors, only silicon atoms are present, or only germanium atoms are present. Only germanium atoms are present. Like this, only germanium or purely silicon atoms are present. Okay. But extrinsic semiconductor, we have to add some impurities to this. Again, intrinsic semiconductors, based on the impurity, intrinsic semiconductors again classified into N-type and P-type. N-type and P-type. P-type. In intrinsic semiconductors, they are purely semiconductor, means semiconductor metals, semiconductor elements. But in case of extrinsic semiconductors, they are having some impurities to conduct the electricity. Means what happens in intrinsic semiconductors, at high temperature, these are act as a conductor, at low temperature, these are act as a insulators. At a room temperature, they are act as a insulator. At room temperature, these are act as a insulator. At high temperature, these are act as a conductor. But in case of this extrinsic semiconductors, at room temperature or high temperature, at room temperature, these two are act as a conductors. Got it? Okay. N type and P type. Next, go to the concept that N type and P type semiconductors. P means positive, N means negative. Got it? P means what? Positive, and N means negative. Okay. Extrinsic semiconductors are classified into, that is a P type of semiconductors and N type of semiconductors. That is, we are studying the P type semiconductor. P type semiconductors. P type semiconductors. Okay. In P type semiconductor, P means positive. P means what? Positive. Means here positive charges are excess. Means electrons are on the, means electrons are deficient. Electrons are what? Deficient. Electrons are deficient. For example, we are taking electrons are deficient, means 13 group elements are boron, aluminum, gallium, indium, thallium, and 14 group elements are carbon, silicon, germanium, tin, lead. Then 15 group elements are hydrogen, phosphorus, arsen, antimony, bismuth. Okay, these are the what? Semiconducting elements. What happened here? We have to add the 13th group elements to the 14th group of semiconducting metals. Semiconducting elements are getting the P-type semiconductors. For example, take a silicon having a tetravalency. Like this arrangement is observed in the silicon. Silicon having a 4 valency means all 4 sides are bonded. Bonded. That's why when we do to the silicon, for example, take anyone, I am taking the aluminum here. Doping of aluminum to the silicon having a 4 valency, isn't it? After doping, aluminum having a 3 electrons in their valence, that's why some space is vacant. Here, some space is vacant. This is called hole. This is called what? Hole. This hole is act as a positive. This hole is act as what? Positive. The what? Mobile. The motion of this movable thing, this is the movable thing. This hole is jumping here, the electron. This electron is jumping here one hole is created. And this electron is jumping here one hole is created. Like this hole in the P type of semiconductor responsible for carrying the current. Okay? In in a p-type semiconductor. How it obtained in p-type semiconductors? Adding or doping 13th group elements to the 14th group semiconducting elements, like getting what a p-type of semiconductors. I am repeating, doping 13 group elements to the 14th group semiconducting metal elements to produce p-type semiconductors. Similarly, n-type semiconductors. N-type semiconductors. Similarly, n-type semiconductors. Same thing, I am removing the aluminum and adding phosphorus. It is the trivalence element. These are the trivalence elements. These are the tetravalence elements. These are the tri or pentavalence elements. Phosphorus, it is a pentavalence element, isn't it? Then it is having a 5 valence electrons in their valence orbitals. Okay. Silicon is a 4 valence element, but phosphorus is pentavalence element. Here 4 electrons are involved in the bonding process. 1 electron remains as it is. This electron is having a negative charge. That's why N type of semiconductor. This electron is mobile in nature. That's why they are continuously mobile, continuously in the motion when it connects to the external circuit. Got it? Here in P-type, holes are the responsible for the charge carrier. In N-type, electrons are the responsible for the charge carrier. Got it? Okay. Next concept is band theory. Next concept is band theory. Band theory. Before going to go deep into the band theory, we have known some basics. What are those? Okay, in our previous classes, chemical bonding, molecular orbital theory we learned. In the molecular orbital theory, atomic orbitals are combined to form one is a bonding molecular orbital, another one is an anti-bonding molecular orbitals. Got it? Okay. In metals, atoms are very close to each other. So many atoms are there. So many atoms are very close to each other in a crystal lattice. That's why their orbitals are also very close to each other. Isn't it? Their bonding molecular orbitals and anti-bonding molecular orbitals are very close to each other. Got it? Okay. The group of means atoms are very close to each other in the lattice. Means it's the orbitals also. It's the orbitals also very close to each other in the lattice crystals. The group of orbitals or valence orbitals are called band. The group of valence orbitals in lattice are called what? Band. Here, two types of orbitals are there. That's why one is bonding molecular orbitals and another one is anti-bonding molecular orbitals. Bonding molecular orbital having the lower energy, anti-bonding molecular orbital having the higher energy. Similarly, bonding molecular orbitals is then one who have a lower energy, it is called valence band. It is called what? Valence. One who have a lower energy, it is called valence bond. One who have a higher energy, it is called conduction band. conduction band. One who having a lower energy is called valence band. One who having a higher energy is called conduction band. In atomic orbitals or in molecular orbitals, when we are calling the bonding and antibonding like that, completely filled orbitals, that is lower energy orbitals are called valence band, and having higher energy orbitals are called conduction band. Got it? Okay. In case of metal, what happened here? This is what? It is a completely filled orbitals, completely filled valence orbitals. This is valence band. Valence band. It is a conduction band. This is a conduction band. This conduction band. Here it is a partially filled valence band. Partially filled valence band. Here partially filled valence band. When electricity is applied, there is a very less energy gap between the partially filled valence band and conduction band. When we apply the circuit, when we apply the electric current, electrons are easily jump from valence band to conduction band, and it conducts the electricity. In case of metal, or in case of completely filled orbitals, completely filled bands means these are completely filled orbitals. What happens here? This is the valence band, filled valence band. Valence band. This is filled valence band. This is the conduction band. Conduction band. Conduction band. In conduction band, see the conduction band. Here, these two bands are overlapping. These two bands are what? Overlapping. This may act as superconductor also. In this case, conduction band and valence bands are overlapping. This makes the what? Superconductors. In case of in case of conductors. And same thing in case of insulators. Same conduction band is same, but this is the energy gap. This is the energy level. Here energy gap is very less. Here completely filled valence band is they are overlapping. But in case of insulators, the conduction band and the valence bands having a large or more energy gap. The energy gap is maximum. Energy gap. Maximum number of energy gap. Energy gap is maximum. That's why when we apply the electric circuit, external circuit to this compounds, it do not conduct the electricity because energy gap is maximum. The filled valence bands containing the electrons cannot jump from valence band to conduction band. That's why this is having the insulator properties or do not conduct the electricity. In case of In case of semiconductor, in case of what? Semiconductor. In case of semiconductor, this is conduction band. This is conduction band. This is conduction band. This is valence band. Valence band. Valence. What happens? Valence band containing electrons easily jumps from valence bands to conduction band because energy gap, low energy gap. Low energy gap. What happens here? The energy gap is very small. That's why electrons jumps from low energy. Electron jumps from valence bands to conduction band. Okay, that's why when I give a temperature to this compound, electron jumps from valence bands to conduction band. Here you cannot, electrons cannot jump from valence bands to conduction bands. Here there is no difference between the energy gap. Actually, there is no difference between the differentiation between the valence band and conduction band. That's why easily electrons are movable. Here cannot. Here some extent giving high temperature it acts as a semiconductors. Okay, it acts as a conductors in semiconductors. Got it? Okay, bye.